So thanks a lot for the invitation. So when I was asked to talk about application industry, I really hesitated on which one to pick. So I decided to pick one which is relatively closely to my heart. It's the first one that we started working when I joined Amazon. And then the second one, which is more like it's a major effort. There was a lot of engineering efforts as well. And so the first one is more browsing new products, and how to have more natural way of browsing products. And the second one is in the forecasting domain. So if I have to pinpoint two take-home messages, or at least two things I would like to communicate, which are relatively simple messages, but about approximate inference and approximate machine learning in industries, that, well, one, I think there are lots of applications and lots of opportunities for applying machine learning, and progressive machine learning in particular. So people don't realize that having predictive uncertainty is important. It's important for decision making, and I think it's something that we need to communicate better, and we need to make sure that we can make that communication and communicate this gap, that there is this potential when you use progressive machine learning. And so I think one of the things that would help when we try to implement those methods is really to keep it simple. So not keeping unnecessarily simple, not simplifying things unnecessarily, but keeping things simple and only complexifying when there's a need, when there's a real return on investment, because in the end, you can think of an ever complex model, and the impact of this additional delta might be minimal. So be very careful when you would like to complexify the solution and make sure that there is a real material impact. So let me start by just talking about the general context. So if you think about Amazon today, in 2017, well, it's much more than just retail, just much more than just selling products. So of course the goal is to be able for customers to find anything they would like to buy, and whatever situations. But it's also a platform where people can sell stuff. So people not only realize that, but of course half of what is sold on the platform is sold by third-party sellers. So the other thing is, if you think about the platform itself, well, there are a whole bunch of services. There's music services, there's video streaming services. There's also services to help you publish books. So there are all sides, additional services that we offer to other types of customers. And then there's also Alexa. And Alexa, for example, when you're a developer, you can think about new applications. There's Alexa skills, and that makes it very powerful to tackle new problems that we haven't thought about, and that are really enriching the whole environment. And then, of course, for developers, there is AWS. You probably know about storage services and compute power, but also now we have Amazon AI services. So trying to put in every developer, in every hand of every developer, where to help them in using and building machine learning solutions and democratizing them more widely. So I think it's very exciting times to be at Amazon at the moment, and it's a great opportunity to have an impact in many different fields. Now, why would we have? How can we have this impact? So it's of course, we can think about those very fancy applications, and there are many very exciting applications. You can think about, okay, we want to solve general AI. But I think one thing to keep in mind is that there's a lot of other stuff that machine learning has an impact on. So there's a lot of applications that are not as visible. There's essentially at the moment machine learning is transformation. It's having an impact on all corners of the business. And that's also why we would like to accelerate that process by offering those services through AWS, for example. Now, to make that happen, to make those applications, to be able to deploy all those machine learning solutions, I'm getting back to my initial point, you need to be careful not to make things too complex. And so you only have to introduce complexity when there is a need to introduce complexity. And there are a couple of reasons for that. There's of course, you want to make sure that you have a return on investment on the time spent in developing those solutions. But one, you have limited bandwidth. And there are tons of very exciting applications we can tackle. It's one of the benefits of machine learning is that it's not always obvious for business people, but there's that kind of generic solution that can be applied in many different situations. Of course, they're specialized, but that's very powerful. That's very interesting for us, because that means we can really jump from different application domains, which is again very exciting and very enriching. The second aspect, that when it's simpler, it's also more robust. Ultimately, solutions are more robust, they're easier to maintain, and it's also better. It's easier to understand when something goes wrong. When you have a model which is in production, it's an overall system, and when someone in the team, that's some engineers, make some changes to the code base, well, you want to have something which is relatively simple that you can diagnose and deep dive into the issue, and so you need to understand all the components very well. And tracing back errors is one way of making that much easier when your models are only the complexity that they need. Okay, so the first example I want to talk about was like understanding fashion and style. So that was one of the first, that's the project that's close to my heart. And it's something that we did very early on when I joined, like about 4 years ago in Berlin. And so the idea was to say, well, okay, we know there are recommendations, there are browsing tools you can have like on Amazon. But when you look at books and you search for books or you search for like media, multimedia, or maybe from some CD, it's very so it's very difficult to, it's not very different from browsing, for example, fashion attributes like apparel, shirts, trousers. And I think if you look at how people buy stuff in that domain, well, if they're in a shop, well, they're going to look through the different items, they're going to maybe look at the material, they're going to look at the color. It's a very complex domain, and there are many, many different dimensions to what's going to drive their selection and what type of things they would like to see or buy. And so the idea was to say, well, maybe we can do much more than just looking at what people have clicked, like for example, clicked on the click-through rate, or what they've bought in the past in conjunction with different items. We can look at something which is more, has some more semantic information, it's more richer information. So we can, for example, look at 3 more to go. So we can, for example, look at images, of course, so we can look at visual information, and that's very rich information for those types of products, but still it's very difficult to have a sense of depth or even know what's the texture. So one domain where you capture that information is, for example, in descriptions. So you have like text descriptions. And you have a whole bunch of other additional modes of modalities, like for example taxonomies, and maybe some external like information about the products and features. So the idea was, well, maybe we can combine all those modalities into a single model, and then try to learn a representation that will help us like browse and discover things in a more intuitive way, in a way that for humans is much more intuitive than, for example, browsing or like searching according to sort of predefined dimension features like brand or the size or color. And so we looked at probabilistic models to do that, essentially because we wanted to build like latent variable models and then be able to capture like the similarities in this latent abstract representation and compute those representations like based on new data that we hadn't seen before. So those are the results that we got out of this approach. So what we have here, what you see is like on the top left, that's a target product, that's like the target address. And so based on that, we just like looked at the whole catalog, which is like huge and did not have like any filtering. So essentially we combine those different types of modalities, have this representation, capture like compute similarities, and those are the top K, like highest ranked items. And what you can see there is that it's qualitative, but what you can see is that it's not only capturing, for example, in some cases color, but it's capturing the shape, it's capturing like the patterns in the dresses. So you have like different aspects that are captured depending on in the different like closest matches. So for example, the first one is more of the pattern is identified. In the second example here, you see that well here there's like this middle like shading area, etc. So we're quite pleased with this result, and so we looked at other products, and we looked, for example, at art. There's such a thing they called Amazon Art, and then here we had like this target product is on the top left. So we have like this first this painting, and then what we get out of this once we learn this representation of similarities, we have this list of unfiltered other pieces of data very similar to the first one. Okay, so you might wonder what do we use for capturing those similarities. So we didn't use deep learning, like some work that started like 3 or 4 years ago. So what we're essentially using is shallow latent variable models. And I think it's interesting to see how even those simpler models can really produce very powerful results. So we try to include like a lot of prior information in how we constructed those models. And so in fact, those models are essentially Gaussian latent variable models. And so you have, in this case, you have like very different views, and then you have n items in your training set. And so in terms of the likelihood, well, it's just like it's sort of a structured likelihood where we have a bunch of different modalities, as I said, like images and text, etc. And then we have a number of latent variables. So we have two types of latent variables. Latent variables that are shared between the different modalities, and latent variables that are specific to the different modalities. So essentially those latent variables that capture some uncertainty and try to identify what is common, and that's actually the representation that you use then to compute similarities. Now we're not only looking at those this kind of abstract representation to the y and 0, in fact, which is a shared representation, but we also want to introduce some sparsity. So for those of you that worked in these types of models, in fact, they know that if you have this Gaussian likelihood, you can impose some constraints on the covariance matrices, and then you can recover different types of models going from factor analysis, principal component analysis, CCA, and some more general versions. So when you learn those representations, you have some rotational ambiguities that appear in this model. And so that's why we decided to look into solutions that are introducing some level of sparsity, where you get rid of those ambiguities. Now, strictly speaking, you don't need to get rid of them, but having this sparse representation helped, for example, at prediction time, because then you get like a very sparse model, which means that prediction is much faster than if you look at these very high-dimensional potential representations. So how does that relate to the workshop? Well, let me go into a little bit more detail about the approximate inference scheme. So it's based on variation inference. Just to get the notation, what I'm interested in is, so you see like the lower bound here. And so we have like a bunch of latent variables and parameters. Here the variables, theta are the parameters, and then we have some double users that are parameterizing those approximate posterior distributions. And so we assume some factorized form to make everything nice and tractable. Okay, so if you want to scale up inference, well, the obvious thing to do is to look at stochastic variation inference. And so one way to look at it is that, well, if you look at the bound that I showed you before, you can write it in two different ways. This is essentially here, the first is the variation E step, and this is the variation M step. So in the variation E step, you try to maximize like some, like the relevant terms of the bound, and you have one, so these are parameters of the variation posteriors for every latent variable Zn. And in the variation M step, well, you do the same thing for the parameters. So this is like in the standard batch variation inference. Now this is going to be slow because n can be very large. So the obvious thing to do is to look at stochastic variation inference. And in this case, well, this is like in a very high level, like very simplistic way, you can say, well, we observe that we have here something which is factorizing in n, and here we just have a sum over n. And so instead of looking at the whole batch, well, we're going to construct like mini batches and do some gradient step, and that would make much more progress faster than doing this, going through the whole data set before you do the update of the parameters. So that's all nice, except that you're losing one major advantage of like EM tags method is that you're losing the lower bound. You're losing the bound that in some sense you lose the fact that like every update is going to monotonically increase your bound at every iteration. And this is like something which is very important when you build like a real system. You want to be robust, you want to be sure that you can double check that everything is right. I mean, double checking is quite painful, but at least at some point when you have all the equations right, well, you know that you have to do the right thing. So the question is whether we can do something which is more interesting than, can we do some modification of stochastic variation inference which would retain, for example, the good properties of standard batch variation inference. And there is such a variant. So this is actually closely related to incremental EM. It's also closely related to a stochastic average variance descent that has been done in optimization. And it was something that I talked about like 2 years ago at the same workshop. So essentially what we do is that we can, if you look at the, what we optimize, we have, look at the likelihood, well, we can maintain like the full batch like over the whole data set. And the thing that really matters is essentially the sufficient statistics. So we need to maintain these sufficient statistics. And so when you look at stochastic variation inference, essentially you do an approximation based on the mini batch. We don't maintain something that over time that you want to correct. And so based on that observation, well, instead of doing that, you can say, well, for every mini batch, I'm going to subtract the previous contribution and based on the sufficient statistics, and then update those sufficient statistics with the new parameters. And that has a nice property of conserving the monotonic increase of the bound. So it's a very small modification, but it's stochastic, makes progress like stochastic variation inference, but it has like good properties. Now, of course, you pay a price for that. So the disadvantage compared to stochastic variation inference is that you have to store something. In many applications, you can store this additional amount of information, not in all cases, but that's maybe not a story. So to give a sense of how this looks like in practice, so we applied it to the previous model, we applied it to topic models as well. And so what you see here is the evolution of the bound as a function of the number of data points that you see. And essentially the blue line is batch variation inference, so you see that you're converging like over the several data sets. So you're converging to a good solution, that is like the bound is increasing monotonically, and it's in fact often going higher ultimately than stochastic variation inference. We do see that SVI is making much more progress much quicker in most cases, but we're losing this, we have this jitter and we're losing this monotonic increase of the bound. And when you look at incremental variation inference, well, you still have progress based on mini batches, but you recover the bound, which is a nice stability check in real life. Okay, so the second application I want to talk about was demand forecasting. So one of the problems that we looked at was how do we predict the demand of products in a relatively long time horizon. So here this is an example of a necklace and the actual underlying demand. So you have like the historical data, its time series, and then you would like to predict at a horizon which is pretty far into the future, like up to one year. It was our goal when we looked at those problems. So it's a pretty complicated problem because, again, the catalog is huge. So you have so many items to predict, and especially when you look at fashion attributes, well, you have to predict for every size, every color. Maybe there are some different minor variants. So it's a very, very big number of products we have to forecast the demand for. They're related in some way. And because this is like there are so many products, in fact the data is relatively sparse, which means that some of the products, or many of the products in fact, are selling infrequently. So you don't observe a lot of data points. So predicting the demand over a long time horizon is pretty difficult. And typically what we like to do is having some expected number of items you will sell in the future. So, well, the forecasting setup is relatively standard. We have like some input data, like the historical time series, and then we like to predict the demand in the future. So because of this sparse data, we would like to have like a probabilistic forecast. So we want to have like distribution, not only the mean or the mode, but then we have distribution around the mean. Like how confident are we in the forecast? And the main reason for that is that then we can, at any point in time, we can like compute some like averages over some time interval and have much better estimates of what we actually need to have in stock to foresee in the next 2 weeks or next month or next 6 months. The other component that we need to have like a way of introducing features. So you don't get all the information from the time series. Typically, time series only have some limited historical span, essentially because like there are a lot of new products, for example, and so many of the things that sell do not sell for 5 or 10 years, especially not in fashion. So you have to introduce some additional prior information that you might have, or features that you might have, to improve the prediction. So those are just 2 examples of why you need the features, which is pretty natural. So the first thing is that this is like, again, on the left we have this time series, so like this is like the future, and so we see that, for example, there's some seasonality, right? There's like some peaks here, coming here, and this these two peaks occur again here, and then we have this happening again in the future. So this is extremely difficult if you only have, for example, to capture it, for example, you have, so this is 2 years of data, but if you have 1 year or less than 1 year of data. So having that additional information is not only going to help your model doing better. But then there are things that are a bit, there are some things that are a bit more questionable. So what we see here, that we have like this natural true demand, we have this second peak. It seems that there was something that happened there, which didn't happen before, and so if we know what that event was, maybe we can account for that in the models in general, in a better way. And so that's why you need like those features or handcrafted features as well as the time series. So getting back to the probabilistic forecast, so this is to give you an idea of what we like to get, is essentially, well, we have the historical data here under the green curve, and we have to predict not only like the demand, which is like in this case, so the actual true demand is the black curve. So after from green to red, you go from past to the future. And so we would like to have like the red line being as close as possible to the black line, but in fact you want to make sure that you have also some measure of uncertainty around that. And so what you see, for example, in and you want this uncertainty to grow over time, because the further down in the future, well, the more certain you should be about your forecast. So one thing that you can see here on the left is that so if you the top right corner, what we see that well, we have the predicted demand, and then which seems to be underestimated. And then in addition, when we look at the uncertainty, we see that most of the time the demand is outside of this bound. So that's also having those probabilistic forecasts is also very important to diagnostic potential issues in your when the things realize in real life. So why does this the model on the top right left is like doing a bad job? Well, essentially there's a time that this red region there in the middle. It's essentially a time where we were running out of stock, so we had no observations. And so again, like having a probabilistic model there, having a latent representation is very useful because you can use like some data imputation during this time interval. And if you don't do that, well, you get well, the model assumes that there is no observation, and what happens is that you underestimate the demand in the future. So when you have a proper probabilistic modeling, well, you can account for that, and then you get the results like at the bottom where we have we've imputed the potential trend of the time series and get much better estimates and much more consistent estimate in the future. So what do we use for in this case? So it's the latent state forecaster. That's the name that we gave you. So if you want to have all the details, you can have a look at the NIPS paper last year by Cedric. But the two main points I would like to discuss is one, the top two lines. So the top line is the likelihood. So what is a good likelihood for such type of models where you have like intermittent demand? So essentially demand where you have lots of not that many observations. And second, the second line, the Y line, is like how do we want to capture information that we put into the latent state? So this is the latent state, and there are essentially two components. There's one on the axis, that are kind of the deterministic component, and then there is like another stochastic component, which is the I, it's called like innovation in forecasting role. So just to sum that up, so you have like two components of this latent state. One on the left, like this deterministic component, which is so this deterministic component based on the features that we have into the model, and then the second stochastic component that accounts essentially for all the externalities that are not captured in the model. In terms of the likelihood, well, if we look at the intermittent demand, so to look at to get like a sense of how difficult the problem, well, here we just have like a histogram of the number, of the number of times a product is sold over some per day. Sorry, and so we see that there's a huge peak on the left. There's a huge peak, in fact, it's so big that we cannot even show you the actual height of that peak. So most of the time, the products are not sold. There's no selling of those items. It's only in a couple of times that those products are sold. So you have like kind of this very very high peak at 0, and that's in fact like 98% of essentially the target farm is R0. So it's a huge problem in practice. And so the way to approach it is to look at like some staged, multi-stage likelihood. So that's one potential solution. We explore like many other ones. But so the way we approach it is that we have like essentially want to construct the likelihood at different steps, and so you have like a decision first a decision between whether something sold or not, did sold or did not sold at least one item, sold at least one item, or didn't sell. Right? So essentially you can introduce like some logistic regression there to make that decision. The second peak is pretty high as well, so we introduce like a second step of staged decision. So we have a second logistic regression that decide whether it's higher than 2 or 1. And then, because then it's much smoother and you can capture another distribution, and the rest is done by a Poisson likelihood. So you have essentially a likelihood which is like a weighted sum of 3 components that kind of fit the problem very well and very intuitive. They are quite intuitive also to communicate to maybe business people. So how do we scale up inference in this setting? Well, there are several options, but after like exploring multiple solutions, what we essentially end up doing is like something which is very like a nested optimization algorithm, where we looked at essentially Laplace approximation of the log marginal, and the Laplace approximation could be done in a very efficient way by doing some Kalman smoothing, and so you have like a linear complexity instead of a cubic complexity, which is very efficient. And so once you do this Kalman smoothing, you find the mode of your posterior, and then you can look, for example, at standard, very powerful optimizers to optimize the parameters of your actual underlying model. Okay, I think I'm running a bit out of time. So I'm almost there. So this is like to give you some of an idea of some of the results. So what we compare to is, for example, this ETS, which is an exponential smoothing, and it's a very popular package by him and others that's used extensively. And so what we essentially see, like this model could potentially include like features, but it doesn't offer that functionality that the package will find online. And so this is, for example, preventing the model to capture some of those peaks that we can nicely capture with the additional features, for example. What you also see, so on the top right is long time horizon. So we see that this is the failing of identifying the peaks. If you look at the 2 ones underneath, that is like short time horizon. And what's interesting to see is that there the model is able to capture those peaks. So in fact, you're starting seeing the benefit of adding those additional variables when you start with the like much longer time horizons. Okay, so to conclude, so one thing I wanted to, one point I want to make is that I think ML, if you don't know that yet, ML is really transformational. It's having like really a real impact on all corners of the business, and that there's like a lot of potential for looking at probabilistic machine learning application as well. But I think the message should be clear, and we should make sure that we communicate the benefit and make that accessible. And sometimes the models are a bit more complex, maybe conceptually than more classical models, and communicating that is a real challenge. So try to deploy things that are like as complex as it needs to be, that will also help in the communication. And so finally, I wanted to acknowledge like my co-workers, Beza, who helped me extensively on the incremental branch inference work, as well as Felix and Michael, who are probably somewhere, and Pablo, who are somewhere at the conference. And then Matthias, David, and Valentin that worked on the forecasting.
Okay, we have time for one quick question.
Thanks for a great talk. So I have a quick question about the incremental processing. It feels like this is essentially equivalent to an EP-like algorithm, where you're deleting the information to the current data point, deleting the statistics out, and then performing an update for the approximation to that. I was wondering whether you thought about ways of making that more efficient by perhaps grouping data points together that were similar, approximating them together, and then maybe that produces the number of sufficient statistics that you need to keep in memory, so you just need to keep the memory statistics lower. And then on top of that, maybe thinking about using scheduling. So scheduling particular updates based on perhaps a measure drive for creation?
So there are many ways of implementing that, and those are what you mentioned, possibilities. So we explored many different variants. Simply, if you want to make a connection between that and things like SAG, then you need to randomly sample a new mini batch every time, which is in practice not very useful. But there you have guarantee. And so yeah, there are many different variants, and depending on how you scale partitioning with the group, whether the way you sample, you get different, essentially, properties of the algorithms. Some are being better than others.
Let's thank our speaker again.